Electrolysis of water is the decomposition of water into oxygen and hydrogen gas due to an electric current being passed through the water. The reaction has a standard potential of -1.23 volts, meaning it ideally requires a potential difference of 1.23 volts to split water. This technique can be used to make hydrogen fuel and breathable oxygen, though currently most industrial methods make hydrogen fuel from natural gas instead. History: Jan Rudolf Dilmen and Adriaan Pares van Troostwijk used in 1789 an electrostatic machine to produce electricity which was discharged on gold electrodes in a Leyden jar with water. In 1800 Alessandro Volta invented the voltaic pile, and a few weeks later William Nicholson and Anthony Carlisle used it for the electrolysis of water. When Zeno Gram invented the Gram machine in 1869, electrolysis of water became a cheap method for the production of hydrogen. A method of industrial synthesis of hydrogen and oxygen through electrolysis was developed by Dmitry Lakhanov in 1888. Principle: a DC electrical power source is connected to two electrodes, or two plates, which are placed in the water. Hydrogen will appear at the cathode, and oxygen will appear at the anode. Assuming ideal Faradaic efficiency, the amount of hydrogen generated is twice the amount of oxygen, and both are proportional to the total electrical charge conducted by the solution. However, in many cells competing side reactions occur, resulting in different products and less than ideal Faradaic efficiency. Electrolysis of pure water requires excess energy in the form of overpotential to overcome various activation barriers. Without the excess energy, the electrolysis of pure water occurs very slowly and not at all. This is in part due to the limited self-ionization of water. Pure water has an electrical conductivity about 1/1,000,000th that of seawater. Many electrolytic cells may also lack the requisite electrocatalysts. The efficiency of electrolysis is increased through the addition of an electrolyte and the use of electrocatalysts. Currently, the electrolytic process is rarely used in industrial applications since hydrogen can currently be produced more affordably from fossil fuels. Equations: in pure water at the negatively charged cathode, a reduction reaction takes place, with electrons from the cathode being given to hydrogen cations to form hydrogen gas. Reduction at cathode, 2H++ 2E H2 at the positively charged anode. An oxidation reaction occurs, generating oxygen gas and giving electrons to the anode to complete the circuit. Oxidation at anode, 2H2O2 plus 4H plus 4E minus. The same half reactions can also be balanced with base as listed below. Not all half reactions must be balanced with acid or base. Many do, like the oxidation or reduction of water listed here. To add half reactions, they must both be balanced with either acid or base. Cathode, 2H2O plus 2E minus H2 plus 2O minus anode, 4O minus O2 plus 2H2O plus 4E minus. Combining either half reaction pair yields the same overall decomposition of water into oxygen and hydrogen. Overall reaction, 2H2O to H2 plus O2 to the number of hydrogen molecules produced is thus twice the number of oxygen molecules. Assuming equal temperature and pressure for both gases, the produced hydrogen gas has therefore twice the volume of the produced oxygen gas. The number of electrons pushed through the water is twice the number of generated hydrogen molecules and 4 times the number of generated oxygen molecules. Thermodynamics. Decomposition of pure water into hydrogen and oxygen at standard temperature and pressure is not favorable in thermodynamic terms. Anode 2H2O2 plus 4H plus 4E minus EOX equals minus 1.23 volts. EO red equals 1.23. Cathode 2H plus 2E minus H2EO. Red equals 0.00 volts. Thus, the standard potential of the water electrolysis cell is minus 1.23 volts at 25 degrees Celsius at pH 0. At 25 degrees Celsius with pH 7, the potential is unchanged based on the Nernst equation. The thermodynamic standard cell potential can be obtained from standard state free energy calculations to find delta G degree, and then using the equation delta G degree equals NFE degree. In practice, when an electrochemical cell is driven toward completion by applying reasonable potential, it is kinetically controlled. Therefore, activation energy, ion mobility and concentration, wire resistance, surface hindrance including bubble formation, and entropy, require a greater applied potential to overcome these factors. Electrolyte selection. If the above-described processes occur in pure water, H+ cations will accumulate at the cathode and O- anions will accumulate at the anode. This can be verified by adding a pH indicator to the water. The water near the cathode is acidic while the water near the anode is basic. The negative hydroxide ions that approach the anode mostly combine with the positive hydronium ions to form water. The positive hydronium ions that approach the cathode mostly combine with negative hydroxide ions to form water. Relatively few hydronium hydroxide ions reach the cathode anode. This can cause a concentration over potential at both electrodes. Pure water is a fairly good insulator since it has a low autoionization. KW equals 1.0 times 10⁻14 at room temperature, and thus pure water conducts current poorly. 0.055 microsiemens cm-1. Unless a very large potential is applied to cause an increase in the autoionization of water, the electrolysis of pure water proceeds, very slowly, limited by the overall conductivity. If a water-soluble electrolyte is added, the conductivity of the water rises considerably. The electrolyte dissociates into cations and anions. The anions rush towards the anode and neutralize the buildup of positively charged H+ there. Similarly, the cations rush towards the cathode and neutralize the buildup of negatively charged O- there. This allows the continued flow of electricity. Care must be taken in choosing an electrolyte, since an anion from the electrolyte is in competition with the hydroxide ions to give up an electron. An electrolyte anion with less standard electrode potential than hydroxide will be oxidized instead of the hydroxide, and no oxygen gas will be produced. A cation with a greater standard electrode potential than a hydrogen ion will be reduced in its stead, and no hydrogen gas will be produced. The following cations have lower electrode potential than H+, and therefore suitable for use as electrolyte cations: Li+, Rb+, K+, Cs+, Bar2+, Senior 2+, California 2+, Na+, and Mg2+. Sodium and lithium are frequently used, as they form inexpensive, soluble salts. If an acid is used as the electrolyte, the cation is H+, and there is no competitor for the H+ created by dissociating water. The most commonly used anion is sulfate, SO2-, 4, as it is very difficult to oxidize, with the standard potential for oxidation of this ion to the peroxy disulfide sulfate-ion being -2.05 volts. Strong acids such as sulfuric acid, and strong bases such as potassium hydroxide and sodium hydroxide are frequently used as electrolytes due to the strong conducting abilities. A solid polymer electrolyte can also be used, such as naphthalene, and when applied with a special catalyst on each side of the membrane can efficiently split the water molecule with as little as 1.5 volts. There are also a number of other solid electrolyte systems that have been trialed and developed, with a number of electrolysis systems now available commercially that use solid electrolytes. Techniques. Fundamental demonstration. 2 leads running from the terminals of a battery are placed in a cup of water with a quantity of electrolyte to establish conductivity in the solution. Using sodium chloride in an electrolyte solution results in chlorine gas rather than oxygen due to a competing half reaction. With the correct electrodes and correct electrolyte, such as baking soda, hydrogen and oxygen gases will stream from the oppositely charged electrodes. Oxygen will collect at the positively charged electrode and hydrogen will collect at the negatively charged electrode. Note that hydrogen is positively charged in the H2O molecule, so it ends up at the negative electrode. Note that an aqueous solution of water with chloride ions, when electrolyzed, will result in either O- if the concentration of Cl- is low, or in chlorine gas being preferentially discharged if the concentration of Cl- is greater than 25% by mass in the solution. Hoffman voltammeter. The Hoffman voltammeter is often used as a small-scale electrolytic cell. It consists of 3 joined upright cylinders. The inner cylinder is open at the top to allow the addition of water and the electrolyte. A platinum electrode is placed at the bottom of each of the 2 side cylinders, connected to the positive and negative terminals of a source of electricity. When current is run through the Hoffman voltammeter, gaseous oxygen forms at the anode and gaseous hydrogen at the cathode. Each gas displaces water and collects at the top of the 2 outer tubes, where it can be drawn off with a stopcock. Many industrial electrolysis cells are very similar to Hoffman voltammeters, with complex platinum plates or honeycombs as electrodes. Generally, the only time hydrogen is intentionally produced from electrolysis is for specific point-of-use applications, such as is the case with oxyhydrogen torches, or when extremely high purity hydrogen or oxygen is desired. The vast majority of hydrogen is produced from hydrocarbons and as a result contains trace amounts of carbon monoxide among other impurities. The carbon monoxide impurity can be detrimental to various systems, including many fuel cells. High-pressure electrolysis is the electrolysis of water with a compressed hydrogen output around 120 to 200 bar. By pressurizing the hydrogen in the electrolyzer, the need for an external hydrogen compressor is eliminated. The average energy consumption for internal compression is around 3%. High-temperature electrolysis is a method currently being investigated for water electrolysis with a heat engine. High-temperature electrolysis may be preferable to traditional room temperature electrolysis because some of the energy is supplied as heat, which is cheaper than electricity, and because the electrolysis reaction is more efficient at high temperatures. Alkaline water polymer electrolyte membrane nickel-ion. In 2014, researchers announced an electrolysis system made of inexpensive, abundant nickel and iron rather than precious metal catalysts, such as platinum or iridium. The nickel metal nickel oxide structure is more active than pure nickel metal or pure nickel oxide alone. The catalyst significantly lowers the required voltage. Applications. About 5% of hydrogen gas produced worldwide is created by electrolysis. The majority of this hydrogen produced through electrolysis is a side product in the production of chlorine and caustic soda. This is a prime example of a competing side reaction. 2 sodium chloride plus 2 H2OCl2 plus H2 plus 2 sodium hydroxide. The electrolysis of brine, a water-sodium chloride mixture, is only half the electrolysis of water, since the chloride ions are oxidized to chlorine rather than water being oxidized to oxygen. The hydrogen produced from this process is either burned, used for the production of specialty chemicals, or various other small-scale applications. Water electrolysis is also used to generate oxygen for the International Space Station. Hydrogen may later be used in a fuel cell as a storage method of energy and water. Efficiency. Industrial output. Efficiency of modern hydrogen generators is measured by energy consumed per standard volume of hydrogen, assuming standard temperature and pressure of the H2. The lower the energy used by a generator, the higher would be its efficiency. A 100% efficient electrolyzer would consume 39.4 kWh per kilogram of hydrogen, 12,749 joules per liter. Practical electrolysis may consume 50 kWh per kilogram, and a further 15 kWh if the hydrogen is compressed for use in hydrogen cars. Electrolyzer vendors provide efficiencies based on enthalpy. To assess the claimed efficiency of an electrolyzer, it is important to establish how it was defined by the vendor. There are two main technologies available on the market: alkaline and proton exchange membrane electrolyzers. Alkaline electrolyzers are cheaper in terms of investment, but less efficient. PEM electrolyzers, conversely, are more expensive but are more efficient and can operate at higher current densities, and can therefore be possibly cheaper if the hydrogen production is large enough. Reported working efficiencies were for alkaline in 1996, lying in the 50 to 60% range for the smaller electrolyzers and around 65 to 70% for the larger plants. Theoretical efficiency for PEM electrolyzers are predicted up to 94%. Ranges in 2014 were 43 to 67% for the alkaline and 40 to 67% for the PEM. They should progress in 2030 to 53 to 70% for the alkaline and 62 to 74% for the PEM. Overpotential real water electrolyzers require higher voltages for the reaction to proceed. The part that exceeds 1.23 volts is called overpotential or overvoltage, and represents any kind of loss and non-ideality in the electrochemical process. For a well-designed cell, the largest overpotential is the reaction overpotential for the 4-electron oxidation of water to oxygen at the anode. Electrocatalysts can facilitate this reaction, and platinum alloys are the state-of-the-art for this oxidation. Developing a cheap, effective electrocatalyst for this reaction would be a great advance, and is a topic of current research. There are many approaches, among them a 30-year-old recipe for molybdenum sulfide, graphene quantum dots, carbon nanotubes, perovskite, and nickel oxide. The simpler 2-electron reaction to produce hydrogen at the cathode can be electrocatalyzed with almost no overpotential by platinum, or in theory a hydrogenase enzyme. If other, less effective materials are used for the cathode, larger overpotentials will appear. Thermodynamics. The electrolysis of water in standard conditions requires a theoretical minimum of 237 kilojoules of electrical energy input to dissociate each mole of water, which is the standard Gibbs free energy of formation of water. It also requires energy to overcome the change in entropy of the reaction. Therefore, the process cannot proceed below 286 kJ per mole if no external heat energy is added. Since each mole of water requires 2 moles of electrons, and given that the Faraday constant F represents the charge of a mole of electrons, it follows that the minimum voltage necessary for electrolysis is about 1.23 V. If electrolysis is carried out at high temperature, this voltage reduces. This effectively allows the electrolyzer to operate at more than 100% electrical efficiency. In electrochemical systems, this means that heat must be supplied to the reactor to sustain the reaction. In this way, thermal energy can be used for part of the electrolysis energy requirement. In a similar way, the required voltage can be reduced if fuels are reacted with water or oxygen ions. This results in some of the fuel's energy being used to assist the electrolysis process and can reduce the overall cost of hydrogen produced. However, observing the entropy component, voltages over 1.48 volts are required for the reaction to proceed at practical current densities. In the case of water electrolysis, Gibbs free energy represents the minimum work necessary for the reaction to proceed, and the reaction enthalpy is the amount of energy that has to be provided so the reaction products are at the same temperature as the reactant. Potentially, an electrolyzer operating at 1.48 volts would be 100% efficient.